All right, now that we're all charged up, we're to 18.5 Coulomb's law. Or another way to describe Coulomb's law is electric forces. This is one of the big sections of the chapter, so buckle up. It's going to be good. Now we get to finally take our knowledge of what happens when we have opposite charges that they attract and like charges, negative, negative, or positive, positive, that they repel. We're going to actually describe that force. Besides the qualitative, okay, it'll attract, repel, how much force is there actually present, right? So if we have a positive charge Q1 and negative charge Q2, there's an attractive force between them, right? Each one is drawn to the other one, and that force is equal and opposite in direction, right? Q1 is drawn to the right towards Q2, while Q2 is drawn to the left, which is now the negative direction. Similarly, if we had two positive charges, Q1 and Q2, they would now experience this repulsion, which is forces pushing away, and they'd again be equal in magnitude, but opposite in direction. Q1 would now be in the negative direction, versus Q2 is now in the positive direction. So that's where we need to fill in the knowledge of attraction or repulsion and how that then would describe the actual direction. But what about calculating the magnitude of this force? Well, I'm glad you asked. If we want to calculate the magnitude of the force, that is where we can use Coulomb's law. Coulomb's law says that the magnitude of this electrostatic force exerted by one point charge on one other point charge is directly proportional to the magnitudes of these charges, how much charge they have, and inversely proportional to the square of the distance between them. That's a lot of mathy language to describe this equation right here, which is one of our key equations. That the electric force is equal to this constant K times the magnitude of one charge times the magnitude of the other divided by the distance between them squared. And that square is really important, so you have to make sure to keep that square in there. Now, what is this K? Well, the K is known as an electrostatic constant, and K, you can note, is just 8.99 times 10 to the positive 9 newtons times meter squared per coulomb squared. Please do not round this to 9.0. That is too much rounding. You need the 3 sig figs here. So keep it as 8.99 times 10 to the positive 9. This is also sometimes written, you'll see it in some books, as 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. And epsilon naught's just another constant. You don't have to have it memorized, you just have to know that it's something you can look up. 8.85 times 10 to the minus 12 coulomb squared per newton per meter squared. I prefer to often work in terms of K. I think K is a little bit simpler. Then you don't have to worry about the 4 pi and keeping it properly in the denominator. So I encourage you to just work with K as is written here. And that will allow you to calculate the magnitude of this electrostatic force. Pretty cool. All right, well, let's try it out with an example. So example 3, a model of the hydrogen atom. In the Bohr model of the hydrogen atom, the electron is in orbit around the nuclear proton at a radius of 5.29 times 10 to the negative 11 meters. Determine the speed of the electron, assuming the orbit to be circular. This is pretty nifty. The Bohr model of the hydrogen atom was one of the first models that actually worked for describing an atom, and it turns out it still works very well for hydrogen atoms. It breaks down as atoms get more complex, but it's a really good basic model for atomic physics, for how the atom works. It's something we'll get to come back to later on, I believe in chapter 30. So something more to come there. But let's take a look at our process here. What do we know? What do we want to know, right? Okay, so on the things that we know, first off, it gives us this radius, right? Numbers are a good thing to note. So it tells us the radius is 5.29 times 10 to the negative 11, very small, meters. They also have already given us a picture, which is very convenient. what are some other things that we know? Well, it mentions that there's an electron and then that there's a proton. The proton is in the nucleus, it's in the center. And so noting those, what do we know? Well, if it's an electron, we know that its charge has to be given by negative E, right? Negative E is that constant that we saw before. So Q, the charge of it, is negative E, or we could write that as negative 1.60 times 10 to the negative 19 coulombs. And then for the proton, we know the charge is equal and opposite. So we can write that the Q is just equal to positive E, or positive 1.6 versus the negative of the electron. All right, so this is already off to a really good start. You notice there's some implicit information hidden in that. What do we want to know? Notice it says we want to find the speed of the electron. So we want to find how fast it's going. Okay. Thinking about that, what tools do we have that might help us out here? I'll jot down over here. Well, one that is probably relevant is Coulomb's law, right? That's the section we're in and we just learned about it. So let's start by writing that one out. And that says that the force between two charged objects is given by K times the charge of 1, the absolute value of it, because we're just dealing with the magnitude, times the absolute value of the charge 2, divided by the distance between them squared. Right, as we're looking at this equation, we know K, that's just a constant, Q1 and Q2, those are the two charges involved, which are an electron and a proton. So we know both of those as well. And R is going to be the distance between the two charges from one to the other. And that will then give us the electrostatic force. So we're in good shape to get the magnitude of the force here. Now, with this equation, this only gives us the magnitude. We then need to fill in the direction. And so the direction, we remember, is going to be along the line connecting them. And which object do we care about? Well, notice we're trying to find the speed of the electron. So we care about what force the electron feels due to the proton. So what's the direction of the force the electron feels? It's going to be drawn to the proton, right? So it feels this inward force right along that inner radius. So that then gives us the direction of said force. We don't have a specific direction other than inward, but just drawing this into the picture is helpful to us, especially as we try to then think about how we can go from having a force to having a speed. So thinking about that, any ideas? How can we relate force to our kinematic variables? Maybe you're starting to think back to 2a, one of our classic hallmark equations that popped up again and again and again, right? What was that? F equals ma, right? Newton's second law, that the sum of the forces has to be equal to the mass times the acceleration. This is a good one to use when in doubt if you have forces involved and you need to connect to the kinematic variables. Now, we aren't trying to solve ultimately for acceleration, but we can think some about acceleration. Does the electron experience any acceleration as it travels around the proton? Noting that the problem mentions we can assume the orbit to be circular. Thinking about circular motion, what do we know about the acceleration? This is another great throwback. If we are in circular motion, we have to be having centripetal acceleration. So for the circular, the acceleration must be given by v squared divided by r. So the force then that the electron experiences, the net force is going to have to come out to mass times v squared divided by r. And we already know r, we're trying to find v. What about m, the mass? Well, remember, we're focused on this electron here and what it's experiencing. Do we know anything about the mass of the electron? Why, yes, in fact, we do. If you remember back in the very first section, we talked about the mass of the proton, neutron, and electron. So here we're going to pull in the mass of the electron. Get a new color for this. That the mass of the electron is, and you can look this up, you don't have to have it memorized, but 9.11 times 10 to the minus 31 kilograms. All right, so now we are actually in really good shape. We can solve for the force that is pulling the electron inward. It's this electric force. We can then, once we know that force, we can set equal to mv squared over r, and then solve for v, and we'll be home free. So let's take a look at that. All right, so solving for the force, we have k, this is 8.99 times 10 to the 9. Then we have the two charges, which both are just the magnitude of 1.60 times 10 to the negative 19. So instead of writing that twice, they just squared it, right? They did q squared here, because both the charges have the same magnitude. And then divide by the distance between them, squared. So that comes out to a force, which we'll remember, what are the units of force? They are newtons. So we'll keep those units there. Then we note that that's the only force acting on our electron. So that force is equal to ma, where the a is the centripetal acceleration, v squared over r. So if we want to solve for v, we can multiply the force both sides by r. That will cancel it in the denominator here. And then we can divide by m. And finally take the square root. Take the square root of both sides, then we'd find that v is equal to the square root of force times radius divided by m. And that is what we have there. So we use our force from the first calculation, we multiply by that same radius, and then we divide by the mass of the electron. And that then comes out to 2.18 times 10 to the 6 meters per second, which are our units of speed. So that part is logical. We're happy with that. And this is pretty quick, right? 2.18 times 10 to the 6. It's flying, but it is not yet moving at the speed of light. So this is a reasonable calculation, right? Speed of light is 3 times 10 to the 8th meters per second. So that's a great upper limit to keep in mind, because once you start getting close to that, things start getting weird. But that is for a later chapter. So this introduces Coulomb's law. In the next video, we'll take a look at what to do with Coulomb's law when we don't just have 2 charges present, but we have 3 or more charges present. So stay tuned.